Okay, this is Math 105, section 1.4. We're going to start by talking about rational expressions. So when we take a quotient of two expressions, okay, we call that a fractional expression. So that's a quotient of two algebraic expressions. And here's some examples. 2x over x minus 1, square root of x plus 3 over x plus 1, and y minus 2 over y squared plus 4. Okay. We talk about a rational expression, we're being a little more specific. Okay. It's a fractional expression where both the numerator and the denominator are polynomials. So in this case, this is also a rational expression because these are both polynomials. But this is not a polynomial, square root of x plus 3, because remember we can only have positive natural number exponents. We can't have x to the 1/2, right? This is also a rational expression, just like the first one, but this one is not. Okay, so here's some examples of rational expressions. Polynomial divided by polynomial. Degree of 1, degree of 1. Degree of 1, degree of 2. Degree of 3, degree of 2. Okay, so these are what we call rational expressions. Think of ratios. Okay, we talk about the domain of an algebraic expression. We think of the set of real numbers that we can use, that the variable is permitted to have. Okay. So when you're talking about a rational expression, think of your denominator. Okay. Because the denominator can't be 0, you can't divide by 0. So wherever your denominator is 0, that's where your domain is undefined. So we can say, okay, the domain for this thing, 1 over x, is just the set of all x such that, we're using our set builder notation there, x can't be 0, right? Because we can't have 0 in the denominator. Okay. For a square root, now that's not a rational expression, but let's say we look at this, the square root. Whatever's inside a square root has to be positive or 0. So here we'd have to say x is greater or equal to 0. So the domain of this would be set of all x such that x is greater or equal to 0. Here we have the same thing, but it's in the denominator, so it can't be 0. Okay, so here would be the set of all x such that x is greater than 0. Okay, so here we want to find the domains. For something like this, quadratic, it's not a rational expression, we can use any x. So we could say domain here, we'll use capital D, is x can be any real number. Okay. For the second one, we'll go to the next page for that, and then the third one as well. So we can see for the first one that, as we said, that x can be any real number. So the set of all real numbers. We can put any x in and get that. Okay. For the second one, think of your denominator, x squared minus 5x plus 6. We don't want that equal to 0 because you can't divide by 0. So we factor this, okay, x minus 2 times x minus 3. And our denominator would then be 0 if x equals 2 or x equals 3. So that would be our domain, is that x can't be 2, x can't be 3. And we could just write that like this, you know, capital D as our domain, x is not equal to 2 or 3. Okay. Now that implies that we're using all real numbers otherwise. Okay, so this really means the set of all real numbers, but we can't use 2 or 3 because that gives us 0 in the denominator. For C, we have two things going on. First of all, we have a square root in the numerator, which means x has to be positive or 0. We also have a denominator of x minus 5, so that means x cannot be equal to 5. So here's how we define our domain. Using set builder notation, the set of all x such that x is greater or equal to 0 and x is not equal to 5. So we have to exclude 5 out of there. Okay. If we were to use interval notation, here's what it would look like. Let me just do interval notation. So that would be 0 with a bracket to 5 with a parentheses, union, or, now I'm defining separate sets, that's why I'm using union, and then I'm going from 5 to infinity. Okay. So this would be how I would define that using interval notation. I'm starting at 0, I'm including 0, going up to 5, skipping 5, and then I'm starting after 5 again and going to infinity. Infinity always has parentheses, remember. And I'm saying include both of these sets, that's what the EU means. Okay, when we simplify a rational expression, what we're doing is we're going to factor both the numerator and the denominator. Okay. And we're using this property of fractions. If you have a common factor on the top and the bottom, they cancel out. So you end up with just the, you know, if you have AC over AC over BC, you have just A over B because C's cancel out there. Okay. So we're canceling common factors from the numerator and denominator. Okay, so for this example, we're going to simplify this rational expression. We'd start by factoring the numerator and denominator. So this is a difference of squares on the top. So the x squared minus 1 is x minus 1 times x plus 1. And then if you factor this quadratic on the bottom, we get x minus 1 times x plus 2. And notice we have a common factor of x minus 1. So we could cancel those out there. Okay, and then that gives us the x plus 1 over x plus 2. Okay, so that's a simplified version of this. When we're multiplying rational expressions, we don't need to find a common denominator. Remember, we just like we did earlier, you can just multiply the numerators and multiply denominators. Okay. But what you can do beforehand is you can look at common factors up and down, diagonally, or up and down in this fraction. Okay, and cross those off before you do the multiplication, and that makes your work a little bit easier. So for example, here we have this quadratic divided by this quadratic and this, degree 1 divided by this degree 1, multiplying two rational expressions. So we start by factoring. So we factor this x squared plus 2x minus 3 into x minus 1 times x plus 3. This is a perfect square. This is x plus 4 squared. We can factor 3 out of this, 3x plus 12. Okay, and then we can't factor anything out of this. Okay, so here we are, and you might want to do this too. Put parentheses around this x minus 1. So if all your factors have parentheses around them, that way you can see where your factors are and where they can cross off. Like I can cross off this x minus 1, x minus 1. I can also cross off an x minus plus 4 here. So let's do that. So I'm going to cross off this one, and then I'm going to cross off an x plus 4 here, and then I just get a 1 there. Okay, because I have two x plus 4s there. Okay, so what I'm left with, and you can see them canceling out here, and they're canceling out here, right? Same deal. Okay, and then what I'm left with is just that 3 times x plus 3 over x plus 4 as my final answer. And keep in mind that you can just leave it factored in the top and the bottom in your answer over here. Okay. When we divide rational expressions, remember we're dividing fractions. We flip the second guy and multiply. Okay, so a over b divided by c over d is a over b times d over c. We flip that second guy and multiply. Okay, so we always do that first, then do our factoring and try to cancel out. Do this before you do your factoring. Okay, so for this example, we have x minus 4 over x squared minus 4 divided by x squared minus 3x minus 4 over x squared plus 5x plus 6. Flip the second guy and multiply first. Then do your factoring. So here we factored x minus 2 times x plus 2 out of x squared minus 4. This becomes x plus 2 times x plus 3. This becomes x minus 4 times x plus 1. And here's where we're looking for common factors. So I can cross off this x minus 4 on the top and the bottom. I can cross off the x plus 2 on the top and the bottom. And then I'm just left with that x plus 3 over x minus 2 times x plus 1. Don't distribute, just leave it factored, and that's your final answer. Okay, when we're adding or subtracting rational expressions, here's where you have to find a common denominator. So notice this already has a common denominator. We have a c in the denominator of both of these, so we were just adding the numerators, right, for this one. Okay. We'll always use the least common denominator. It's the easiest, and it saves you a lot of work, when you do that. So we can find the LCD by factoring each denominator and taking the product of the distinct factors using the highest power that appears in any of the factors. So that's important that we do that, using highest power that appears in any of the factors. Okay, so we'll look at examples of that in the next slide. Okay, so first example, we're adding 3 over x plus 1 plus x over x plus 2. Now these are already factored, so what you may want to do there is just put parentheses around those to show that they're factored already. Okay. And then when we put those together, we can see we have the x minus 1 factor and the x plus 2 factors are common denominator. So if they're already factored, just put parentheses around them, and then we need both of these for our lowest common denominator. Okay. So for the first fraction, we need x plus 2 times x plus 2 on the top and the bottom. Okay. And then for the second one, we need x minus 1 over x minus 1 on the top and the bottom. So we can get that common denominator of x minus 1 times x plus 2. Don't factor these x plus 2's out. Don't factor these x minus 1's out. You need those so you have that common denominator. So it is tempting to cross those off, but don't, because we put those there for a reason. We put those so we could have a common denominator. Okay. Now we keep that common denominator factored and we distribute on the numerator. So 3x plus 2 is 3x plus 6, and this is x squared minus x. Okay. So we keep this factored, but we unfactor the top. Simplify the top, and then try to factor the top to see if we can simplify that fraction for our answer. Now this we can't factor anymore. We say that's a prime quadratic, so we can just leave it like that. So this is our answer, that x squared plus 2x plus 6 over that x minus 1 times x plus 2. Leave your denominator factored. Okay, for our second example here, we have 1 over x squared minus 1 minus 2 over x plus 1 squared. Okay. So factor, this is already factored, but we can factor the x squared minus 1 as the difference of squares, so that's x minus 1 times x plus 1. So here's the factored denominators. Now we look at the factors on each side. We need the x minus 1 because it's in this one. We need the x plus 1, it's in both of them, and we're going to pick the highest power of that. So we're going to need x plus 1 squared in our LCD, okay? So we need both of these factors, but we're going to need a square on the x plus 1 because we have a square over here. So we always pick the highest power for your least common denominator. Okay. Okay, so what we had to do is we had to multiply x plus 1 and x plus 1 on this one. Okay. And we had to multiply x minus 1 and x minus 1 on this one to get the common denominator. So that's how we got to this step. Okay. And then, again, keep your denominator factored. Simplify your numerator, so we're unfactoring that. So x plus 1 minus 2x plus 2, because we have a minus 2 times a minus 1. Okay? And then that gives us 3 minus x when we simplify that numerator on the top. Keep your denominator factored. This thing's already factored, so no common factors here, and we're done. That's our simplified fraction. Okay, compound fraction is where the numerator and the denominator or both are fractions as well, are fractional expressions. Okay, so it's a little more complicated, but there's actually an easy way we can deal with this, and we'll look at that. So here's an example. We have x over y plus 1 over 1 minus y over x. Okay, so there's two different ways to do this. The first way, what we'll do is we'll do this numerator first, and then do the denominator. Okay, so x over y plus 1, we have to have a common denominator, right? So our common denominator is going to be y, right? So this would be x over y plus y over y, which is what that 1 is. So it's x plus y over y. And then for the denominator, which we do separately, we're going to have a common denominator of x. So this is going to be x over x minus y over x, which is x minus y over x. So there's our first step for that part. So we're going to have x plus y over y divided by x minus y over x. And so that we're dividing two fractions, right? So remember, when we're dividing fractions, we can flip the second guy and multiply. So that takes us to this step. Now we have x plus y over y times x over x minus y. So we flip that second fraction. Okay. Now here's where we look for common factors up and down, okay, or diagonally. Okay. If you get confused, just do this. Put parentheses around your factors. You can even put around the x and y if you want. Okay. That way you can see that those are factors and they're already factored. And then we can see, yeah, there's no common factors here. These are not the same, these are not the same, and there's nothing common factor here. Be careful, you can't divide a y here or an x here, because these are your factors, x plus y and x minus y. Don't tap into your factors. You can't break into them, right? That's why it's helpful to put parentheses here, so you can say, hey, these are locked. I can't divide a y there because I have an x plus there. I can't divide an x here because I have an x minus y there, okay? So putting parentheses kind of locks those up, so you can't get the x out of there, you can't get the y out of here, okay? And because it's an easy mistake to make, okay? Then our final answer is we're just multiplying these, so x times x plus y and y times x minus y. Just leave them factored, okay? So that way we can see, you know, that we don't have common factors, and that's our answer, okay? The second method is to find the LCD of all the fractions in the expression. Then multiply numerator and denominator by it, okay? This is a little bit shorter way of doing it, kind of a shortcut, okay? So in this example, the LCD of all the fractions is xy, okay? So here's our compound fraction we started with. Look at all your denominators. Now this, we could say, okay, technically we could put a 1 under this and a 1 under this. We don't have to, but it allows us to see what the denominators are. Our denominators are y, 1, 1, and x. So our least common multiple of all those four denominators is x times y. Okay. So what we do is we take that x times y, we multiply it times the top and the bottom. Okay. And what that does when we distribute is it cancels all those smaller denominators, that x, the 1, the y, the 1, right? So what we do, we get that is we get x squared if you multiply xy times x over y. And if you multiply xy times 1, you get xy. And then on the bottom, if you multiply xy times 1, we get xy. And then xy times minus y over x would give us minus y squared. Okay? So do you see what happens when you do this first step? It's a little more complicated, but it gets rid of your small denominators right away. And now you just have a basic rational expression. Okay. Now we're going to factor out here. So we can factor out an x of this. So this is x times x plus y. And then we factor out a y here, and that's y times x minus y. And we get the same answer that we did before. So this is another way. It's not like one method is right, one method is wrong, whatever you prefer to do. Okay, if ever you have a denominator of the form a plus b times the square root of c, or anytime you have a square root or a root or radical in the denominator, we want to get rid of that in the denominator. We don't want to have that there, okay? So what we do is we look at our conjugate radical, okay? Now our conjugate radical looks just like it. The only difference is that you, instead of a plus here, you have a minus here. So you switch the sign in front of the radical, okay? If you have a minus here, you change it to a plus. If you have a plus, you change it to a minus. And the reason for that is because, think of our difference of squares, right? If I multiply this times its conjugate, that square root goes away, okay? Because what I'm taking is a squared minus b times the square root of c squared, right? Which is b squared c, okay? So that difference of squares thing, using the conjugate gets our difference of squares, and that makes that square root become not a square root, right? Because we're squaring it. So that's the idea there, is we multiply it times the conjugate radical, and we get rid of it. So if we do that in the denominator, we also have to do that in the numerator. So for an example here, we have 1 over 1 plus the square root of 2. Our conjugate radical is going to be 1 minus the square root of 2. And so we multiply the top and the bottom of that times that conjugate radical, 1 minus the square root of 2. Okay? And you can see it cancels out our square root of 2 on the denominator, which is what we're trying to do. We don't want the square root in the denominator. Okay, so this would be 1 minus square root of 2 times 1, which is just 1 minus square root of 2. And then this is just a squared minus b squared. So we're taking 1 squared minus square root of 2 squared. When we multiply times the conjugate radical in the denominator. So this is going to be 1 minus 2, right? So we get 1 minus square root of 2 over 1 minus 2, which is minus 1. It's also a bad idea to leave negatives in your denominator. So what we can do, well, if you're dividing by minus 1, it's the same as multiplying times minus 1. So we're just taking the opposite of this, which is just switching the order of the subtraction. So simplify this to, 1 minus square root of 2 over minus 1 to square root of 2 minus 1. Just switching these. Okay. And the reasoning for that is this. If you have a minus b, and you take the opposite of that, you just get b minus a. Okay? Or we could say, a minus b over minus 1 is b minus a. So that's kind of what we're using there. These are the same thing, basically. Okay? Divide by minus 1 is the same as multiplying times minus 1. Okay? So when you have subtraction, and you change it to the opposite, you're just switching the order of subtraction. That's the idea there. Okay, here's some common mistakes you want to avoid. This is the correct property. A times b squared is a squared times b squared. But that's not true for plus, so be careful. A plus b squared is not a squared plus b squared. You can't distribute that square on an a plus b. Okay. A times b square root, we can break that out as square root of a times square root of b. Okay. But you cannot do that with a plus. So if you're adding or subtracting inside a square root, you cannot break those out. Be careful of that. Okay. Now this is true because of the property above here, because this is square root of a squared times square root of b squared. You can't do that here, so be careful with that. Okay. 1 over a times 1 over b is 1 over a times b. That's just multiplying fractions, right? But here we can't do this. You can't just add the numerators, add the denominators, or just add the denominators, right? We have to find a common denominator of a times b for this, right? So be careful of that. Let's look at what that would be. That would actually be, we'd have b over a times b plus a over a times b. This is what it should be, okay, for this one, right? Because we have to take a common denominator of a times b. Okay, so we multiply times b and b for this one. We multiply times a and a for this one. Okay, and then we would say b plus a over a times b. Okay. A over B, or AB over A, we can cancel out the common factor of A here, right? So we just get B, okay? But you cannot do that here. Be careful. You know, technically, this is a factor. So I cannot divide A here and A here, okay? So that does not go away, right? So be careful. You cannot divide the A there, okay? This is kind of properties of exponents, but A to the minus 1, B to the minus 1 is just A times B to the minus 1. But be careful, this is not true. A minus 1 plus B to the minus 1 is not A plus B to the minus 1. Kind of the same idea here, that you can't, when you're taking an exponent, you can't, and you're adding inside a parentheses, you can't just break those out. Here's where we can show how these don't work. Let's say we have 2 and 2 for A and B. You know, 1 over A plus 1 over B is 1/2 plus 1/2, which is 1. But if you take 1 over A plus B, you get 1/4. So you can see, here's an example where it doesn't work, right?